All right, let's just dive right into this ultimate exam prep explainer. Today, we're completely tearing down the OSI Reference Model's network layer. Whether you're studying for your CCNA, diving into cybersecurity, or you're a software dev wanting to understand the actual magic behind the internet, we're going to transform these complex networking concepts into some really clear visual takeaways.
It's the classic question every network engineer faces, right? The internet goes down? Who do we blame? Well, before you start blindly troubleshooting cables or panicking over DNS errors, we really need to understand the absolute backbone of global data delivery, and that's Layer 3. If Layer 1 is the physical road, you can think of Layer 3 as the entire logistics and navigation system, making sure your data actually reaches its global destination.
So here's our game plan for today. 1. What is Layer 3? 2. IP addresses, IPv4 versus IPv6. 3. How do routers work? 4. Essential protocols. And finally, 5. We'll wrap up by solving some classic exam questions. Let's get into it.
What is Layer 3? Let's start with the fundamental role of the network layer, the third tier of the OSI model. When you send a WhatsApp message, it obviously doesn't just magically teleport to your friend. It goes through very specific stages of encapsulation. This comparison absolutely nails the difference between your local network and the global internet. Think of Layer 2, the data link layer, like the internal hallways of an apartment building. It uses MAC addresses to find a specific door, say your exact smartphone on your home Wi-Fi. But Layer 3? Layer 3 acts like a massive cargo company. It uses IP addresses, which are more like the main building address, to decide which city or which entire network the data needs to travel to across the globe. Now, you've probably heard the term packet a million times, right? Well, this is where it's born. When data comes down from the transport layer, it's just called a segment. But once Layer 3 slaps an IP header onto it, which contains the source and destination IP addresses, it officially becomes a packet. This packet is literally the ultimate vehicle carrying your data across the internet. Section 2. IP addresses, IPv4 versus IPv6. Moving on to logical addressing, let's look at how devices actually find each other globally, because without a logical address, routing packets would be completely impossible. Okay, the crucial point to take away here is that we literally ran out of the 32-bit IPv4 addresses. Think about it. There are billions of devices on the internet, and IPv4 just couldn't hold them all. That is exactly why the massive 128-bit space of IPv6 was developed. It provides a virtually unlimited address space. We're talking enough addresses for every grain of sand on Earth. It's essential for the future of the internet and completely eliminates the need for annoying workarounds. But wait a second. If we ran out of IPv4 addresses years ago, how on earth is the internet still working right now? The answer is NAT, or Network Address Translation. It's this clever trick that hides all your home devices, your phone, your laptop, your smart TV, behind just one single public IP address provided by your ISP. It basically translates all your private local IPs into one public IP, which has literally saved billions of addresses globally. Section 3. How do routers work? Let's move over to the hardware that actually makes Layer 3 function and see how this builds our network. The absolute star of the show here is the router. Whenever you send data out, your device follows these exact 4 steps. First, it creates the packet. Second, if the destination isn't on your local network, your device sends it straight to the default gateway, which is usually just your home router. Third, the router checks its internal routing table to figure out the best path forward. And finally, the packet hops from router to router until it reaches its final destination. I actually love this concept. Imagine a packet getting lost and just bouncing between 2 confused routers forever. That's where TTL, or time to live, comes in. Without it, a lost packet could circle the globe infinitely and eventually crash the whole internet with endless phantom traffic. Every single time a packet passes through a router, that TTL counter drops by 1. If it hits 0, boom, the router simply deletes the packet. Crisis averted. Section 4. Essential protocols. Because Layer 3 isn't just about IP addresses and routers, it has its very own set of critical protocols that control, organize, and diagnose all that traffic. Whenever you open up a command prompt and use ping to check if a server is online, you're directly using ICMP. You're sending an echo request and just waiting for a reply. Another amazing tool is Traceroute. It actually manipulates that TTL counter we just talked about to map out every single router your packet hops through to reach its destination. Pretty cool, right? It's also vital to know how data actually flows. So normal web browsing, that's Unicast, a one-on-one conversation between you and a server.
But if you're streaming a live sports event with thousands of other people, the network relies on multicast to efficiently send one stream to a specific group. Anycast is also brilliant. It routes your traffic to the absolute closest server geographically, which is exactly how massive content delivery networks keep your load times so fast.
Now, to easily figure out which part of an IP address represents the overarching network and which part is the specific device, engineers use subnetting. CIDR notation, like writing a /24 at the end of an IP, is really just a clean shorthand to carve up that address space. It tells the router exactly where the network ID ends and the host ID begins.
Section 5. Solving classic exam questions. All right, let's put this all together. If you're studying for an exam, definitely pay close attention here. We're going to do a rapid-fire session of the most common questions your professor or CCNA examiner is absolutely going to throw at you.
Exam question 1. What's the fundamental difference between the network layer and the transport layer? This is a classic trick question, designed to see if you really understand the boundary between layer 3 and layer 4. People mix this up all the time.
Here's the trick to remembering this. Layer 3 gets the data to the correct building using an IP address, but Layer 4, the transport layer, gets the data to the correct specific application using a port number. Basically, Layer 3 cares about the destination machine, Layer 4 cares if the data goes to your web browser or your email client.
Exam question 2. Why does packet fragmentation occur and what causes it? Well, think about trying to force a massive sofa through a tiny doorway. You've got to break it down, right? Networks work the exact same way.
And this perfectly illustrates the concept of MTU, or Maximum Transmission Unit. For standard Ethernet, this is usually 1,500 bytes. If your data packet is bigger than this MTU limit, the router has to chop it up into smaller fragments. While this makes sure the data actually gets through, it sadly decreases performance and bumps up the risk of data loss.
Exam question 3. How do routers actually know where to send the packets? I mean, a router isn't psychic. When a packet arrives from Turkey trying to reach a server in Germany, how does it magically know the shortest path?
The secret is all in the routing tables. Now, static routing works totally fine for tiny office setups where an admin can just type in the routes manually. But the entire global internet? That relies on dynamic routing. Protocols like OSPF find the shortest paths internally, and BGP acts as the routing protocol for the whole internet, automatically navigating outages and finding the absolute best routes on the fly.
Exam question 4. What is ARP, and why is it necessary if we already have IP addresses? This is a brilliant crossover question that bridges Layer 2 and Layer 3. Sure, you have an IP address, but to physically send data across a local wire, you need a MAC address. ARP, the Address Resolution Protocol, is simply the translator that resolves a logical IP address into a physical MAC address so the data can actually leave your network card.
I'll leave you with this final thought to ponder. If Layer 3 routing completely vanished tomorrow, what would happen? Well, your phone could technically still talk to your smart TV over your local Wi-Fi using MAC addresses, but your connection to the rest of the world, you would instantly cease to exist. No routing, no internet, no global communication. Layer 3 really is the invisible map connecting our modern world. Thanks for hanging out with me for this explainer, and keep on learning.